then right going forward, let's just look at yeah, let's just kind of look at the activation functions, right. So now that we have a condition that now that we know that, right, a gradient descent is a way out for us to be able to, right, minimize, and we still have not talked about, just looks like we can compute dou L by say dou theta irrespective of how many layers you have and so on. There is an elegant way to do that, which is what actually propped up all this this activity in say deep network, what is called a backpropagation algorithm, which I think we will at least be able to give the schematic today, and then next class I think we should be able to we should be able to show how it works. But the activation functions are now sort of important, okay, because these are the ones through which you are going to introduce a nonlinearity, right. So until now we saw a step kind of thing, right, what is called actually a heave side signal, right. So where you had something like 0 and then right it jumps up to 1, so you have x and then right f of x, and for x let's say less than 0 it is 0 and f of x, and when x is greater than 0 it is equal to 1, and at x equal to 0 you can say it is undefined. Some people might say if it was a Fourier series, what would that be? If you approximated this by a Fourier kind of transform, not Fourier series, Fourier transform, what would you get at x equal to 0? Half, right. But here, right, people don't worry so much and all, right, about that value. Some people will say that right at f of at x equal to 0 I'll take it to be 0, or somebody will say I'll take it to be 1. Okay. Now this is actually heave side, but then the thing is, right, because of the fact that you need to be able to take dou f by dou x, right, along the way, and right, and because at this point, right, it is not differentiable. What will it be? I mean, if you actually went ahead and can you do f dash of x at 0? If you kind of did that, right, what would you get? Delta, right? But then, right, delta and all is not something that you can implement in an architecture, right? An impulse is okay to just understand mathematically, right? But not here. Okay. Now, so which is why this heave side and all is not used, right? That we used in the beginning just to make the argument for some simplicity, right? But really this is not the one that is used. Then there is something called sigmoid, right, which has been around for a long time, but again it is not the one that is most commonly used. Okay. Initially I think there was a lot of hype around it, but then all that kind of settled down. Okay. Now this guy is like f of x is equal to 1 by 1 plus e raised to minus x. So this is 1 by 1 plus e minus x, right. And what do you have? So then, right, I mean if you plot this guy, right, so at x equal to 0 it is half, right. This is x versus f of x. So at x equal to 0 it is 1 by 2, right. So it is half, and then at x as x tends to right a negative a large value, then this will go down, and then as you then go up, right, x becomes a positive quantity, you are hitting 1, right. Okay. This is actually this is called a sigmoid. Okay. And it is nice because it gives you all values between right 0 and 1, therefore it looks like a probability kind of thing, right. This looks like a nice thing to use because it takes values between 0 and 1, and f dash of x, right, what will that be? So f dash of x, right, what is it? So minus e power x, right, e power x by 1 plus e power x by 1 plus e raised to minus x the whole square, right. And then so we can write this as 1 plus e power minus x, right, minus x. So 1 plus e raised to minus x. So let me just add and subtract, and then you have 1 plus e raised to minus x the whole square. So you get 1 minus so you have 1 plus e raised to minus x, right. So you have 1 by 1 plus e raised to minus x for this, and then minus 1 by 1 plus e raised to minus x the whole square, right. So 1 by 1 plus e raised to minus x is actually f of x, right, itself. Okay. That is this guy. What happened? Did I make a mistake? This is okay, no? So then f of x minus this is what? 1 by 1 plus e even. So, this is f square f x, right. So, this is like f of x into 1 minus f of x. Okay. So, f dash of x, why we are talking about it is because that is what which use gradient descent derivative and all, right, will actually enter, okay, into the picture. Therefore, we should know what it is. So, if you try to intuitively see, right, it looks like a derivative is initially increasing, right, and then after you hit x equal to 0, it starts to fall off, right, eventually goes to 0, and on the left again it goes all the way to 0. So what do you expect? I mean, it would look like, I mean, so f dash of x, and if you try to see how it will look like, so that's going to, so at 0, what is it, 1 minus 0.5 into 0.5, that's like 2.25, right. So, at 0 it is 0.25, and then it's got to be like that. On either side it will go down to 0. And right, and why this matters is because, you know, when you take this gradient, right, which is what is involved in the step, when you move forward or whatever, right, during your gradient descent, this one, right, iterations. Then if the slope really falls off, right, then it means that for large values of x, right, you won't even move much, right. That's what it's showing, no, because the gradient is very low. So if you take an x which is very low, which means on the other side, right, negative side, it's very low, or on the positive side, if it is very high, it looks like the gradient, right, for those points are going to be very low. Therefore, it then means that you could get stuck somewhere, right. You won't be able to move forward much because the gradient value itself is very low. That's also the reason why sigmoid and all, right, is not really a prominent. I mean, if you look at these hidden layers, right, you won't find sigmoid and all right in the first initial layers and all. If at all, probably, right, they come much later, because if you throw them right at the beginning, then you will encounter issues of this kind, where if your x is very large, either way, right, if the, let's say, magnitude of x is large, you are in trouble, because the gradient then is small for, large magnitudes of x. But there was a time, right, when, let's say, right, people thought sigmoid was right, it was everything. Of course, right, that doesn't mean that people don't use it in the initial. I'm saying generally not. Okay. You may find some network where they've done it, and then, right, you should not tell me that, hey, look, right, you said that, but then they're using, right. Then okay, then the next one is what is called tan hyperbolic. Okay, and tan hyperbolic is what, sin hx by cos hx, right. So, it's some e power x minus e power minus x by e power x by e power x plus e power minus x. Okay, this is another sort of an activation. Okay, let me just ask you a question, right. Can you have anyway, I mean, right, I don't expect a straightforward answer, because, this is kind of a tricky question. Can you have any kind of nonlinear function as an activation? I mean, right, I'm showing a few, I'm going to show you sigmoid, Heath side we saw, right, and then maybe tan hyperbolic, it will be like -1 to 1. But, right, in general, of course, right, one thing is that, okay, I think, maybe we'll again ask this question, right, after we do this. Okay, let's just finish this, then we'll come back. Okay, then what happens is, so as x goes negative, all right, so as x goes negative, so you have like -1, right. So as x goes negative, that term survives, whereas the first two terms will drop off from numerator and denominator, and at x equal to 0, it's 0 by 2, right. So, okay, so it goes like that, right. So, it goes like 1 to -1 f of x, and it goes via 0. So, this is f of x versus x, right, and at x equal to 0, it is 0 to 0. And I'll just leave it to you as actually an exercise that a derivative of this. I mean, so if you call this as f of x, then f dash of x is 1 minus f of x whole square. These are all simple things, right. You guys know how to do this. And again, if you try to plot this, right, f dash, then at x equal to 0, it's 1, right. And yeah, and whether you go this way or that way, because you're squaring it, right. So, it can go down on either side, and right, and you get this. So, this is your f dash of x. Again, right, this also has a problem that is somewhat similar to sigmoid, right. That means, for large magnitudes of x, yeah, right. So, slope will be small. That means, you have a gradient. Of course, I am not drawing it correctly, it is all symmetric, right. So, this, right, a gradient will then be small, okay. Therefore, not really a great thing to use. Then the third one, which is the most commonly used, is ReLU. Okay, this is called rectified linear unit. Rectified linear unit. Okay, ReLU. I mean, RE taken from here, L and U taken from there. Okay, rectified linear unit, and right, this looks like this. So, you have x, you have f of x, and f of x is actually max of x comma 0. Okay, so which means that on the positive side you have a slope 1. So, whatever is x, right, that is also the value of, say, f of x. Negative side, it is simply 0. Okay, so it means that, right, so it means it won't even allow negative values to kind of go forward, right, because it simply clamp them to 0. But then the nice thing about this is that for, let us say, the positive x, right, it will, I mean, you do not have a gradient. So if you try to plot f dash of x, what will that look like? It will be a step, right. So it will be like this, and then has a value 1. So it is f dash of x versus x, so on. So strictly speaking, at x equal to 0, f dash is a kind of undefined, but then people just take it to be 0, right. So f dash of x is 1 for x greater than 0, and 0 for x less than or equal to 0, or some people may say the other way. Okay. Again, right, that is simply because you want to be able to go forward and kind of use it, right. Otherwise, I mean, you will be stuck. Now, there is also something called leaky ReLU, right, which means that right, I mean, if you do not like the fact that you are completely clamping all the values to the positive side, so what you can do is you can have what is called a leaky ReLU. That means you let something leak through, and that will look like this. So you have a small slope, right, on this side, and then of course, right, and then you have the slope of 1. Let us say this is x, and then this is f of x, right. So you allow for this one, a positive slope, right, but then a small value. Okay, so that right, you, even if x takes some negative values, you still allow them to survive, right. You don't just knock them off. And this will be like, suppose let's say I take this to be some beta, then f of x is max of, what is that, beta x comma x. And of course, right, if you try to take the gradient, so this will be like what, beta constant here, and then jumps up to 1. And this is f dash. Okay, that's how it will be. So this leaky ReLU is used, okay, quite often. Okay. Okay, now suppose I right, come back to that sort of a question, and then okay, there are some other variations also. No problem, right? We don't have to do, right, I mean, every one of them. But let me ask you this question. So now, right, see some of them have what are called, some of these are called squashing functions, in the sense that they don't allow, for example, if you look at sigmoid and then tan hyperbolic, they are called squashing, because they don't let the output go beyond, let us say, -1, 1 and so on, right. So that is called squashing. ReLU is not like that, right. On the positive side, you can go as much as you want with the slope 1. Oh, slope is equal to 1, right, not x. I don't know how I wrote slope equal to x. The slope is 1. Okay. Yeah, I mean, if I write something, I mean, sometimes, right, I have something in my mind, and then I may not write the same thing writing there. So if I make a mistake, let me know. Okay, now, so what was I saying? So now, can we use any kind of a nonlinear function as an activation function? Suppose let us say sine. Can I use cos, sine? Why don't they use that? I mean, again, I will see that again. There is no theoretical great answer and all, right, which I have, and I haven't seen one. But there is some reason, right, which seems to be a reasonable reason. What do you think? What is the, I mean, okay, now, yeah. So the idea is that, right, I mean, there is something about these functions, right, which is common, Huh? I mean, so the answer is this, right? So the activation function should be a monotonic function. Otherwise, I mean, right, you can ask, I mean, can you not use a sine or cos? But then the problem is the output will start fluctuating, right, which you don't want. Okay, again, right, I'm saying, right, theoretically, it's not like somebody has proven that, because in fact, I read somewhere that somebody has shown that sine can all still be used. You get it? I mean, right, empirical evidences you cannot, somebody says that, look, I've used it and then I still get something. But normally you don't see it, okay, you don't see in sine, you don't see sine or a cosine or something, you don't see any of that. The right reason being that you kind of, you would like the activation function to be a monotonic function. In fact, right, that's why I wanted to wait for this, right, before I again went back to the right universal approximation theorem. Actually, the original form was such that, right, you should be a squashing function. The original UAT, right, no, the activation function that you used had to be squashing functions. But then it's only a sufficient condition. Okay, that's why you have ReLU, right? It's not a squashing function, right? ReLU. Yeah. I mean, the squashing means you have to kind of bound the value somewhere. They cannot just go on. Whereas ReLU will allow it to go to any value, right? But I think as recent as I think 2-3 years ago, somebody then came up with actually a proof for ReLU that the universal approximation holds. But then before that, right, if you read the actual theorem, it would say that it should be a squashing function, right? And then the other thing is that regarding the value itself, right, that you wanted the output. I think yesterday, right, I was trying to point out that at the output layer, whether you should have an activation. So, for example, this is f of x. What should it be? So, for example, if it's a classification problem, very likely that you will have a sigmoid sitting there at the output layer. Okay, so like I said, you have sort of in between you could have many layers where probably you have ReLU and all that, but then towards the end, okay, if you have a classification problem, typically expect a sigmoid to be sitting there. If it's a regression problem, typically expect a ReLU to be sitting there, or it could be simply a simple linear unit. It does not have any other activation. It can also happen at the output, right? Again, as I said, the universal approximation theorem says nothing about what should be in the output layer. The activation and all is for that single layer, right, which is this one hidden layer. It's all about that. But in our examples, we took, of course, activation to be in the output neuron also, right? We took all that, but that's why the output neuron, right, whether it will be simply linear, it can also be totally linear. It doesn't have to have an activation at all. It can have activation of the type sigmoid. It can have activations of the type ReLU. It does not have to have activations at all, also, right? So you can have networks of all types. Okay. All right. So now the point is, right, now to sort of go back and say that, okay, now I have some inputs, right, x1 to xn, and then I have, let's say, right, hidden layer 1, hidden layer 2, hidden layer 3, whatever, right, I've got, let's say, right, 50 layers, and then out comes my output layer. Okay, so this is my input layer, then this is a bunch of hidden layers, and I have an output layer, right? Now what do I want? I want to be able to solve for my weights and the biases, which are all sitting here, right? So weights and biases are here. So the biases are sitting in the neurons, and the weights are all in those interconnections that are going from the output of the previous layer to the input of the next layer. So you want to find all of that, and you want to be able to solve. So at the output, right, you have a cost function L of theta, where theta is the weight and the biases. Okay, that's like the whole network, weights and biases, right? So the idea was that how does one solve it then, right? I mean, you may love to have a deep network, but then you should have a way to train it, right? So this backpropagation, which is basically a derivative chain rule. That's what it is. Back propagation algorithm is the one that. So backpropagation, right? So this is 1986. So this backprop is actually a systematic way to, and see, these days, right, nobody even writes down these equations, right? Because if you see the way these things are structured, these packages, that you just define the cost function, it does everything else for you. If you use PyTorch or you use TensorFlow or anything, but I think we should, at least in our life, we do it at least once, so that we know, right, how it works, right? And so the backpropagation is what I want to do next. So it kind of looks like this. Okay, so as an example, right, I'm going to take a simple example, but this example will help, right, illustrate how this whole backprop works. So I'm just going to take a 2-input case. And the first this one hidden layer, and I am trying to take a fairly general case so that we understand. Okay, I am going to take 4 neurons. I think let me make them a little bigger. Okay, I am just blowing it up. Then I have a second hidden layer where I have got 3 neurons. Then I have an output layer where I have got 2 neurons, right, which is okay. So that means, right, we are not taking a very simple case for something that you can explain in class, right. This is enough. Oh. Let me just so x1, x2. Okay, and I am going to write down a few things here now. Okay. Now I am not going to show all the weight connections, but let me say that, right, this will get kind of say connected to this. Okay. So this goes there, this goes there, this goes there, and these weights, right, I mean, I will just show for, okay, now let me also put something here. I will tell you, right, what these things mean, okay. And then, so this is input layer, I am going to call this as L equal to 1, okay, and all these things will matter, and this will be L equal to 2, this will be L equal to 3, this will be L equal to 4, okay, and I am going to write this thing as Z1. So the first neuron, I will write it as Z1 2 because this L is 2. So each is like this is like ZIL, okay, and BIL. Okay, so you kind of think about it like that. Oh, sorry, AIL, not BI. This is AI. Okay, so what this means is this is like A1 2, and then this will be like Z2 2. It's not square, okay, just Z2 2, then A2 2. Z2 2, A2 2, then Z3 2, okay, because this neuron is the third neuron. This will be A3 2, Z4 2, A4 2. So, okay, then similarly here this will become Z1 3. So this will be like Z1 3 because L is 3, okay. Z1 3 first neuron, therefore it will be A1 3, then second neuron, therefore Z2, then the superscript is for L. Z2 3, A2 3. Then Z33, A33, what will be the fourth one then? So we should write it as Z14, A14, Z24, A24. As long as you can understand this sort of a notation, we are fine. And then let's call this as output. Let's call this as Y1 hat. Let's call this as Y2 hat. Okay, and okay, and then this weight. Okay, so this is the first neuron, right? So let's call this as W. Okay, now each of these branches weights will be like WIJL, and B, the bias, right, we will indicate it as B, what is it, BJL, no, BIL, okay, yeah, I, because I is the first neuron, second neuron, and so on, right. And you know what, then what will typically, right, people write as a +1 here, okay, there will be a +1 here, +1 here. Why do you think you need that +1? Because there is a bias term, no. So these weights will get weighted. You have W1 x1 plus W2 x2 W plus a theta 1, right, and that is the theta 1 is this is +1. That means there is actually an arm, right, going from, what to say, right, I mean see, there is let me show it by a different color. So, right, I mean you have like kind of one arm going like this, a plus. So which means that you have B1. So for example, right, this is L equal to 2, right. So this bias will be, right, B1 2. This bias will be B2 2. The bias here for this is neuron will be B3 2 and then B4 2, right. So the Z is actually that linear weighted combination plus the bias. I mean Z is like, you know, summation Wij xj plus theta plus bj. Anyway, right, I mean, we will revisit, you do not have to worry too much, but I hope you understand this +1 is to just indicate the bias, okay. But we will not show these arms going because then it will make it very complicated, right. So I am just going to remove, but just believe, right? Remember that everywhere this +1, so the +1 will mean that the bias for the neuron, right, going ahead, okay. And then, so in that sense, right, this will be like not W1 W111. Okay, this will be, this is the second neuron, first right, input from the first input. So right, W21, this will be like W311, this will be like W411. So I am just following the same this one notation that we used earlier. We are not changing that. Then what will be the weight here then? How will you write this? So it should be like WIJL. So, what will be the first weight? W, okay, now W11 2, right, and this will be like okay, W 2 2 2 and so on, right. So, you should understand now, right. I mean, if I had given the other weight, then it would have been W 2 1 2. So, I mean something from here to there, it would have been W 2 1 2, right. So, as long as you understand the notation, right, it's fine. Okay, then finally, right, I am just going to write something as delta 1 2, that is right. So, delta 2 2. So, all this is like delta IL. Okay. So, this is like delta IL. So, I will stop here. Okay. And then this will be like delta 3 2, this will be like delta 4 2. And similarly, this will be like delta 1 3, delta 2 3, delta 3 3, and then this will be like delta 1 4, and then this will be like delta 2 4, and all these things are still there. Okay. So, this weight connection and all is there. So, this will be like W1 1 1, and then you will have 3, right, W1 1 3, and then W1 2 3, whatever, right, all that is still there. Okay. And then the bias will be a BIL, right, I told you that already. Okay. So, I think I will stop here today.